This is a continuation in a series of video segments that I'm doing for using the Catia V5 program to simulate the lumped single degree of freedom system. And I'm doing these two videos for 2 degree of freedom system. If you can do it for 2 degree of freedom system, any number of degrees of freedom can be handled. However, I call them the killing a fly with a series with a Canon series because the purpose of the Catia program is not to do problems of this type. These are simple problems that can be done analytically by looking at any vibrations book. But my philosophy is that if you can't do these problems in the code, there is something wrong. Okay, it is very unlikely that you can successfully do uh, actual complicated three-dimensional problems in it. Now, here's the situation. I have two lumped masses like that, and the values are given. They're attached together by stiffnesses or springs with these stiffnesses. And what we like to do is to find the natural frequencies of vibration of this lump parameter system. Now, later on in other video segments, I will take the same problem and do a free vibration problem. In other words, move one of the masses and let it go, and these things go back and forth, and so we will do a free vibration problem, and later on I'm going to come and do a force vibration problem. But the first step in any one of these are based on finding natural frequencies successfully. That's because the Catia's transient response analysis or harmonic response analysis is based on linear dynamics, and that requires the calculation of the natural frequencies in the first place. Okay. So the process is very simple. You can write the equation of motion. The stiffness is right here. The stiffness matrix is here. Mass matrix is there. And you find the infamous characteristic equation and solve for the frequencies, and you get these two natural frequencies. Now, when it comes to modeling the spring elements, there are different options, and the one that I could not actually make it to work was this thing called uh, rigid spring type of element. So these work. I'm going to show you, for example, this one. Okay, well, these things will also work, but I could not make this one to work. Maybe I don't know how to do it. Okay, so let's go ahead and do that. We go here, and I'm going to create 3 points. The first 2 points is going to be where the first spring sits. The second 2 points are going to be where the second spring sits. Now, the actual coordinates of these points are totally irrelevant, but actually these can be done where everything's collapsed to one point, but I want to see my springs, so I'm going to make it like that. So let's say second point, I'll make it 100 millimeters away in the y direction, and the third point is going to be 200 millimeter in the y direction. Good. Then I'm going to create points between these, lines between these. So this is going to be my first line. This is where the spring of stiffness 24 Newton per meter. This one. That's going to be this one later on. And then another line which is going to go from here to there. This is where the second spring is going to sit. Now, unfortunately, in Catia, if you want to use these spring elements, the way I'm showing it to you, you have to create a mesh made of beam or some other elements. I use beam elements here. Now, that being the case, I want a single element there and a single element there, beam element, and these should be should have a common node. So to do that, first I'm going to make sure that these two elements, these two lines are joined together. This is so that when I create these dummy beam elements, there is no gap in between them. There are no duplicate nodes. So let me go to generative shape design and use the join option to join these two lines to a single line, so that when I mesh it, there won't be a duplicate node at this juncture. So let's see now. So it's going to be this line and that line. You're going to join it, and that's pretty much it. And if you want, you can go back to the part design. Really, it doesn't matter. You don't have to. You can do things from here, but I'll go back to part design. The only purpose of going to that workbench is to join these, which incidentally it could have been done in the wireframe and surface design workbench, but this is fine. Now let's apply a dummy material to this thing, aluminum, metal aluminum on this part. Okay. However, the properties of aluminum, I'm going to artificially reduce them to be 0.1 and 0.1 for Young's modulus and density, so that they don't interfere with my stiffness of the spring. Okay. So this is the actual property of aluminum, 70 gigapascal. I'm going to make it 0.1 Pascal, artificially drop it down by several orders of magnitude. And this is the density for aluminum. I'm going to change it to 0.1, so that is almost no mass, basically. Now we're done here, so we're going to go to the generative structure analysis. These are exactly the same steps that we followed in the single degree of freedom system. Now, incidentally, I want to do a frequency analysis, but first I do a static analysis, put a dummy load here, make sure that the deflection is calculated correctly. In other words, my spring stiffness and everything is correct. So I will do a static analysis first. Now, I have to mesh this thing with beam elements. So we're going to go to beam elements. And because I joined it, when I select it, the entire thing is selected. And I'm going to put a minimal mesh here. In other words, one element there, one element there. So minimal mesh. And in fact, if you want to look at your mesh, it's going to go like that. Right-click mesh visualization. There's going to be two elements with a common node. And the only reason we got a common node is because I joined it. Notice that this is element 2 going between node 3 and 2. This is element 1 going between node 2 and 1. Now, if I had not joined this, there would have been a duplicate node here, and I had to handle it a different way. Okay, now we're going to do the, what is that, 1D property. I'm going to put it on, well, we can put it on 1D mesh, or we can put it actually on, let me do the following actually. Let me deactivate this. And then 1D mesh. I'm going to put it on this. And it's a dummy circular cross section. I mean, you can change this if you want, but it's not going to come into the calculations. Now, we're done here. So let me now create my connection. Now, first thing I'm going to do, I'm going to hide these points. Okay, so we're going to go and do an analysis connection, which right there. These are exactly the same steps that we took in the single degree of freedom case. A general analysis connection between this point and, for the second component, that point over there. If you're not sure which vertex you're selecting, we can hide this. Oops, I guess you can't hide that because they both go. So just select this one. That's the first connection. And for the second connection, it's going to go between this point, and for the second component, not the edge, not the edge, not the edge. Let's try it again. This point. Okay, so this is going to be my second connection. Okay. Now, the next step, as we did it in the single degree of freedom system, you go to distant connection property right there. You recall that distant connection property. At the very bottom, it says user defined distant connection property. You click on it. Now we will use the spring rigid, okay, not this, spring rigid right there. Oh, sorry, what did I have? Yeah, spring rigid, and this one I'm going to turn into rigid, right there. Okay, so here, this is the one that I'm using. I'm sorry, that's not what I said. I said we're going to be using spring rigid. Okay, so let's change that thing. Oh yeah, spring rigid. Yeah, spring rigid. And these are going to be rigid. So you click on this. The stiffness of this one, this is going to be my first one. It's going to be 24. That's this spring here. Move this thing out of the way. And for the actual support, I'm going to use the first connection that I created right there. Good. And then the next one is going to be another one. This is going to be the second connection. And again, spring rigid, and click on the wrench. And for the stiffness in the direction Y, we're going to put 3. Okay. So basically, I did this one is 24, and this is 3. Okay, good. Now the restraints, this end is clamp. This is moving in the Y direction, just the Y direction. You can see that's open. And this point is also moving in the Y direction. And to check the stuff that I did, this is a static problem. I'm going to put a 1 Newton force here and find out what the deflection of it is going to be. From elementary strength of material, notice that what we have here, let me first put the load there. A dummy load of 1 unit here in the direction 1. Now, notice that when we go to this diagram, these two springs are in these two springs are in series. Okay, so you find the effective stiffness between the two springs, K1 times K2 divided by K1 plus K2. So that is going to come out to be 2.77 Newton per meter. So if you put a dummy unit of 1 Newton here, that 1 divided by the stiffness, which is 2.77, is going to give you 0.325 meter deflection. So if I don't get that, there's something wrong. Let's go ahead and run it. And the deflection should be, maximum deflection should be 0.325 meters, or 325 millimeter, 375 millimeter. Yeah. What I meant was 0.375 meter, and right there, so 375 millimeter. Okay, so we know that we haven't done anything grossly wrong. Okay, fine. Let's deactivate this. I don't want to see it anymore. I don't need it anymore. Okay, now we're going to do insert a frequency case. It's the restraints or the reference restraints from the static case that we did, just right there. And we say, okay, a frequency case has been created. If you double click on it, the default is extracting 10 frequencies, but this is a 2 degree of freedom system. As a matter of fact, let me run it for you, showing that it's going to give us an error message. So when we run it, it's going to come back and say, hey, I don't even have 10 frequencies to be extracted. This is a 2 degree of freedom system. So this is why I go there and change this thing to 2, and then I say okay, and now run it. And lo and behold, we won't get any error messages. That's good. So we go to sensors, frequency, double click on this, and you're going to get your 2 frequencies, except that this is not what I have here, just because I forgot to put my masses there. Whoa. Okay, so let's go ahead and put our masses at these 2 locations. So here is a distributed mass at this one point. 9 kilograms, and then another one at this 1.1 kilogram, and now we're going to run it. By the way, notice that those dummy frequencies that came out, that's going to be based on the frequency of those aluminum properties, basically. So, but anyway, double click on this. There we are, 0.225 hertz, 0.318 hertz. So that is exactly what we have here. So getting frequency is very simple. You just make sure that you don't ask too many of them, if there are not that many, and everything worked out fine. You can change these things. You're getting the same answer. This one I couldn't get it to work, so I'll leave it to you to find out what the issue is here. Yeah, good luck.